Hello, everyone. In this short presentation, I will be lightly discussing my topic for the first mini paper in this class, which is on the subject of the structuring seen in honeybee hives, specifically the hexagonal truss sort of structure, which they naturally build. As a mechanical engineering student, the structural properties of a hexagonal lattice is something that I have considered before, but never in the frame of reference of the beehive. So that's why I decided to look into this topic. So let's get into it. To start off on answering the question of why hexagons, one has to look at what an optimal construction would mean for the bees. In short, it should be the most space efficient and be structurally sound. Each of these two base requirements has a few things that it entails. For the usable space to be considered maximized, the structure chosen should completely fill the space in which the bees wish to construct their hive in what is known as a geometric tiling, and the structure should allow for the most use of the space it creates by the bees. It can't leave a bunch of little pockets, really, that the bees aren't able to either fit themselves or resources into. Then, as far as structural strength is concerned, two key factors are the ways that the stresses manifest in the cell walls due to the way of the hive and the material strength of the beeswax itself that the cells are made out of. I'll now be going into what all this means and how these factors come together to warrant the characteristic hexagonal design we're all familiar with. First, I want to clear up a little bit about what I said on the previous slide when talking about the space usage due to the shape of the cells. When it comes to tiling something, what this means is that the chosen shape completely fills the space that the bees are working with. Irregular tiling specifically means that all the shapes chosen are uniform, which really only leaves three options of triangular, square, and hexagonal cells. As a side note, other parallelogram shaped cells could be used, but in principle, these are all isomorphic to the square cells. Then moving on to what I mean when I say looking at usable space, I wanted to consider the most restrictive thing that would be going into the cells, which is the bees themselves. Nectar and pollen would realistically fit into almost any cell shape, but the bees are all nearly identical in size and shape and cannot really be compressed. So I decided to model them as cylinders with an average diameter of 5.5 millimeters, which is roughly the maximum width you'd find on a bee when its wings are folded in. With this, the usable cell area can be represented as the green circles seen here on the right, inscribed into three different cell shapes. The unusable area, therefore, is the difference between the total area of the cell and the area taken up by the bee. Now, on to actually evaluating the performance of the different cell shapes, I assumed that I would be using regular tilings, like I said on the last slide. The reason for this is in the picture on the right here, where, for example, say I used pentagons and we'd be left with the voids between the cells that couldn't be used. And my second assumption was that the cells would be form-fitting to the bees, creating a minimal amount of unused space possible. And the results were pretty clear that the hexagons were the best, with only around 9% of the cell being unused, whereas the values for the triangle and square cells were much higher. And you may be asking yourself at this point if this result is trivial. I mean, it should be pretty obvious by inspection that a hexagon is the closest available shape of the circles that I used to represent the bees, but that's where the stress analysis that I mentioned at the beginning comes in. And before jumping to the assumptions and results here, I just wanted to clear up exactly what I mean when I say stresses. Mathematically, stress is defined as force divided by the area it's acting on. For example, something like tire pressure in PSI is a form of stress. Inside the hive, then, as gravity pulls down, what's called tensile and shear stresses get built up in the walls of the cells, which try to both stretch them in the case of tensile and tear them in the case of shearing. When something undergoes any amount of stress, it will deform either elastically or plastically, depending on the magnitude of the applied stress. Elastic deformation is generally okay because this is usually reversible and non-damaging to the actual structure. Plastic deformation, on the other hand, which occurs once a particular value called the yield stress is surpassed, is bad and usually leads to structural failure. For this analysis, I wanted to consider a natural hive because these are supported largely from the top and don't have the added stability provided by manufactured hive bases. I also chose the extreme case of a heavy hive supported by very little area from a study which I found, which reported a distribution of quite a few natural hive dimensions across many different hives. I also assumed complete uniformity of the cell construction and stress distributing properties and referenced some average values of the yield, tensile, and shear stresses of beeswax. After decomposing the stress due to the hive weight into its tensile and shear components, these are the maximum resulting stresses. I should note here that I looked at multiple different orientations of the cells, and I'm only reporting here the average values across all of those different ones. Now, not knowing what these units means is okay. If you remember your unit prefixes, the symbol that looks like a U means micro and carries with it a 10 to the minus 6th power, compared to the yield stresses, which are in units of mega and kilopascals, meaning 10 to the positive 6th and positive 3rd, respectively. You can see pretty clearly that the stresses that the wax takes on in even an extreme case such as this aren't even close to what is required to cause failure. And now to wrap this presentation up, I just want to summarize that hexagons are the ideal construction for bees because they make the best use of the space, both that they occupy and provide, and because their construction significantly distributes the stresses that a beehive undergoes, even when it's full of honey, resources, and bees. In the future, to further supplement this topic, I think it would be interesting to look at the thermal properties of wax because it tends to have it bend and peel away from itself, as seen in the top right pictures. And I also think it would be important to conduct a more realistic analysis, realizing that the cells in an actual hive are not all uniform. There are drone cells and even non-hexagonal ones where two different sections of comb get joined together, as you can see in the picture on the bottom right. But anyway, that closes out my presentation, and I hope you learned something, and thanks for listening.